Hi guys, today we're going to be looking at how heat can be transferred from one object to another. And we're going to be looking specifically at heat capacity. And so first, let's talk about energy itself. So kinetic energy is the energy of mass in motion and is associated with the random motion of atoms and molecules. Thermal energy is a kinetic energy, and like other forms of energy, it can be transferred from one substance to another or one object to another. And when objects absorb heat energy, their molecules get really excited, right? So they're going to start moving at a more rapid rate. And as they move more rapidly, what happens is the energy that's contained in the system is going to increase, okay? And so as that energy increases, they can then overcome the intermolecular forces that are holding the objects together. And at this point, they reach something called their melting point, and they can change phases, okay? So we can go from a solid to a liquid or a liquid to a gas at this point. And so, but how does that thermal energy affect balloons? We're going to be making fireproof balloons today. And so when we apply the heat from, say, a candle or a lighter, in my case, I've got a lighter, to the rubber of a latex balloon, the thermal energy from the lighter is going to be transferred from the lighter to the latex of the balloon. And so what's going to happen is the molecules that make up the latex of the balloon are going to get really excited, and they're going to keep increasing in kinetic energy until the rubber reaches its melting point. And at this point, the latex is solid structure. It's going to break down, it's going to weaken, and it's no longer going to be able to withstand the pressure of the air inside it that's pushing on the walls of the latex balloon to get out, and the balloon's going to pop. Okay? So in order to run this experiment, I've got a couple things. One, I've got a regular latex balloon. Okay? This one is just filled with air. I just blew it up, tied it up, it's good to go. The second part that I have is I have my balloon that is filled partway with water and partway with air. Okay. Same latex balloon, same package. Well, not same like balloon, but same package of balloons. I just have put a little bit of water in the bottom and filled the rest up with air before I tied it. And then last, I've got my regular barbecue lighter. Okay. And so what's going to happen? Well, our typical balloon, we said, is filled up with air. Okay. And so if we know that air has a low heat capacity, it's about 1.00 joules per gram degree Celsius, which means it doesn't absorb heat very much. It doesn't absorb it at a rapid rate. Okay. And so that means it's going to be a poor conductor of heat. And so why is this important? Well, what happens is the air inside the balloon is not going to absorb the heat from the lighter that's being put onto the latex. So that means the latex is going to bear the brunt of all that heat, and it's going to absorb the thermal energy, and it's going to eventually reach its melting point, and it's going to pop. Now, and I'll show you what that looks like right now. So I'll put my notes down there real quick though. So let's just take a peek. So here's my balloon with my air, and so here's my lighter. Hopefully light it up. And oh, good. Oh, and there it goes. It pops. Okay. So now, what is going to happen when we do it the same experiment, but this time with a water-filled balloon? So let's talk about water. Water, in contrast to air, does have a high heat capacity. It's at 4.18 joules per gram degree Celsius, which means that it is going to absorb the heat at a rapid rate. This means that it's a good conductor of heat. And so why is this important? Well, the heat energy of the flame is going to be transferred to the balloon, and it's going to be transferred pretty rapidly, okay? And so this is going to cause a smaller increase of temperature in the latex, which means it's going to keep the temperature of the balloon below the melting point, and the balloon's not going to pop. It's going to prevent it from popping. Okay? And so what happens then is, since the water inside the balloon is kind of whisking away the heat from the latex into the water itself, the warm water in the balloon where it's being heated up is going to rise to the surface, and it's going to be displaced with colder water. So it's going to create what's called like a convection current within the balloon. Hot water is going to rise, cold water is going to sink. And it's going to do that continuously until the bulk of the water is heated and there is no more cold water left to keep sinking. Okay, so till it's basically warmed up until it can't conduct heat away from the balloon anymore. And at that point, that's when our balloon will more than likely pop. Okay. All right, so let's take it. Here's my balloon with water in it. Okay. Hopefully I can get my barbecue lighter to cooperate with me. And there's my flame, so here it is. See, I'm holding that flame on the balloon. I'm going to burn it. You can see the soot where the coming off the flame as we're burning carbon here. So we're making soot, but it's not popping. That's it. Fireproof balloon. Okay, so there's all the soot cover, so it's not popping. What happens, however, if I take my flame and put it right here at the air-filled space? Do you think it will pop, or do you think it'll be still fireproof just because it has water in it? Let's find out. So there's my flame again. This time I'm going to hold it to the air-filled space above it. And just like that, it is popped. All right. I hope you've enjoyed my demonstration. This is interactive concept number 4.